Good afternoon or good morning. This is Mrs. Walker, and today I am going to share with you a lesson, The Nature of Science. We are going to start out our COVID-19 semester with a review of information we already have, and then we will go into a lot of other different topics that will get us through the rest of the year. I hope that all of you are safe and that all of you are well. So, the nature of science. Today, we're going to review the nature of science, and you're going to work on a week-long project. You want to make sure that you take the quiz on Canvas and complete the worksheets for this project. You will need your iPad and common household materials for this project. So all you really need for the first part of this project is your iPad and yourself. You're going to need yourself too. So the method of science. We have gone over the method of science. And if you took home your interactive notebook, you have this section in your notebook. So we know that science is a process of observation and investigation to gain knowledge about nature and events. We know the scientific method. It's not one set thing, but it's a way that scientists use an organized procedures to find answers to questions. So the steps of the scientific method, we have a hypothesis, experiment, control, constant, independent, and dependent variables. We know that there's a difference between a scientific law and a scientific theory. So we have a scientific law as a rule of nature that sums up related observations like the law of gravity, or a theory that's based upon experiments like the black hole theory. So now we're going to watch a review video of the scientific method.
It's 2020, the world's gone mad, and the team you manage is all over the place. Monday.com will help. We've gotten the question before, so have you always loved science? For my sister, science wasn't love at first sight. She started to develop a love for science after she started discovering ways it was relevant to her life. But for me, yes, I have. And one thing that really brought science alive for me as a kid was the science fair. We realize not every school participates in a physical science fair, though there are actually online science fairs that you can participate in, if that's something you want to explore. Basically, a science fair is an event where the student comes up with a problem that they investigate, and it's common that the steps of the scientific method are used to investigate the problem. You've likely heard of the scientific method. It is typically presented in a linear set of steps. In my science fair, it went like this. I made an observation of some type of phenomena, and then came up with a question, which was stated in such a way that it could be investigated scientifically. I made a hypothesis, which is a suggested testable explanation for the phenomena. Then I planned out my experiment, which has a procedure of steps that I followed. The experiment turned out to be really exciting, although I'm not sure my parents would have agreed, but I digress. Then I had an analysis where I analyzed the data I had collected. I presented my data in graphs and tables. Then I made a conclusion, which also addressed my original hypothesis. There was only one problem. I got really stuck on the misconception that this particular linear sequence of steps that I did for my science fair was the only way scientists do science. Actually, I thought that was all there was to it, like a recipe for making a cake. I didn't understand that scientists frequently do not work in the linear sequence. Scientists often have to go back through steps or take a different turn or ask new questions. Scientists frequently develop models for phenomena and have to evaluate those models and adjust accordingly. See, there isn't just one universal scientific method that all scientists use. I mean, even if you do a search for the phrase scientific method online or in a textbook, you're going to also find variety. Some include a research step or a separate prediction step that's not part of the hypothesis. Some take out steps. I sometimes wish I could go back to my younger self and tell her that I don't think those steps are written in stone for how science works. But the scientific method did help me reflect on experimental design by serving as a foundation for how a scientific process can work. What I loved most about science fair and going through these steps was that I got to explore something I was curious about. And curiosity matters a lot to us, and many who love science, because it is by exploring these curious questions about phenomena that can lead us to all kinds of new learning. So that gets me thinking really of the nature of science. The word science is derived from Latin, meaning knowledge. Science has the major goal of gaining knowledge, regardless of which branch of science we're talking about. Working in science leads to the development of scientific theories and scientific laws, which we have an entire separate video about. Let's talk about some important terms in science that one could encounter if conducting a scientific investigation. We'll use an example that we had used with our infographic a while back. Have you ever heard of barnacles? Adult barnacles generally do not move in our filter feeders. Many attach themselves to objects, or even animals like the whale we mentioned in our ecology video. Some species will also attach themselves to boats, which might not sound like a big deal, unless you got a lot of barnacles on your boat. Then you could have a problem. I could make observations about the barnacles. This is gathering data. I could count them, identify where on the boat they are attaching, or describe their appearance. I might ask questions about these observations. I might also make inferences. Inferences are logical statements that can be based on evidence I've gathered. For example, if I observe there are a lot of barnacles on the boat that appear very different from each other, and I am aware that there are many different species of barnacles that live in this area, I may infer that there is more than one species of barnacle represented on the boat. With more observations and further study, however, I may need to change my inference. Let's say I wanted to test the effect of different concentrations of a new eco-friendly additive that may prevent the attachment of barnacles. This hypothetical eco-friendly anti-barnacle additive can be added to eco-friendly boat paint. I might do some research about the species of barnacles in the geographical region I am in, and how barnacles attach to boats. I might research details of the ingredients in the additive that I'm wanting to test. When researching, I want to be sure to cite my sources on this. But if I type this into a search engine and automatically pick the first thing that comes up without checking whether the source is credible, that could be problematic. Scientific papers are a good place to start my search. They tend to be peer-reviewed before being published in a journal. This means that the author's peers, that is, other scientists, evaluate their paper. But it's also important to know how to read a scientific paper critically. Check out some further reading suggestions for improving your ability to read a scientific paper. If I were to set up this experiment, I should have a control group. A control group is a group that does not receive the treatment. The thing is, you have to ask yourself, what is the treatment? Because once I know that, I can make sure the control group doesn't get it. So the treatment in this example is the anti-barnacle additive. So while my experimental groups will be boats that receive different concentrations of the anti-barnacle additive in the boat paint, the control group will just get the boat paint alone, without the extra anti-barnacle additive. I will still use the same type of application tool on all groups to put the paint on. You might wonder, why did I include that detail? Well, it's ideal to keep as many other variables the same as possible. I want to rule out that using the tool or the paint application process itself is not having some type of additional impact. I want to ensure that I'm only really testing the effect of the different concentrations of the anti-barnacle additive. All the variables that I try to keep the same are called constants. Other constants would include using the same boat models and same boat sizes. The boat should be kept in the same environment and left for the same amount of time. If I do some graphing of my results, there are a lot of different graph types to consider. I'm going to use a bar graph. Let's say I obtain data after 12 months and I want to graph my data. With graphing, it's important to identify my independent variable and my dependent variable. I would place my independent variable on the x-axis. The independent variable doesn't respond to the other variable. It's independent. In this example, the independent variable would be the different concentrations of the anti-barnacle additive in the paint. The other variable is my dependent variable, and it goes on the y-axis. The dependent variable responds to the independent variable. This could be the number of barnacles observed. Where independent and dependent variables go on the graph, by the way, can be a bit tricky to remember. There is a popular mnemonic known as dry mix that can help you remember the dependent variable or responding variable is placed on the y-axis. The manipulated variable or independent variable goes on the x-axis. When performing this experiment, I am investigating how the independent variable on the x-axis might cause changes in the dependent variable on the y-axis. So you can see this as a potential cause and effect where the independent variable is being investigated as a potential cause to the dependent variable, the effect. Is my hypothetical graph here flawless? No. I would need numerical labels with units shown, graph titles, and repeated trials. Also, it's likely we could improve this hypothetical experiment itself if we could collaborate with others who are knowledgeable about this, especially since we are not experts on barnacles or boats, or barnacles on boats. Before we end, just a few last things about science to fit into this short video. Science can only be used for phenomena in our natural world. Ethics is an important discussion to have when doing work in science. Science is for everyone, and it is a global endeavor. Science is collaborative, and it allows for creativity. Oh, and science is not done. What I mean by that is, Petunia once told me that in school she'd read in her textbook about these scientists throughout history and what they discovered or explored, and she thought that science, for the most part, was done, all discovered, finished. But it's not. Please know the work of science is happening every day, from life-saving medical treatments to potential solutions for environmental concerns to understanding the universe that surrounds us. There is so much we're still learning all the time. And that's why science communication, good science communication with credible sources, is so vital when there is new information gained, as well as our ability to evaluate it. And because science is for everyone, understanding the nature of it is paramount for everyone. Well, that's it for the Amoeba Sisters, and we remind you to stay curious. Treseme's new pro.
So, now that we've watched that video, we're just going to go over quickly the standards of measurement, and we will talk about the standards of measurement more in our lesson for next week. But the International System of Units, or the SI units, that's how we measure things in science. And that's how most of the people in the world measure things. You will see assignments for this week to help you practice scientific measurement, in addition for you collecting data this week. So we measure length, volume, mass, density, and time in standard units. And we have these standard units, and then they're broken down into common prefixes. Graphing is a way that we display information visually to make it easy for us to understand the data that we have collected. We have line graphs that can show a trend or change over time. We have bar graphs where we're comparing information by counting. So in this activity, you will have the choice in this project that we're going to complete over this week and next week. You will have the choice in showing your data either as a line graph or a bar graph, and we will go over those. We also have circle graphs or pie charts, and those are used to show a fixed quantity, meaning that we have 100% of something and we want to show the different parts of that. So now for your project.